Hello. In this section, we will talk about the convergence of a series with positive terms, and we will focus on one of the tests, integral test. So before we start, let's look at some quick notes. We did realize probably so far that in order to determine whether the series is convergent or divergent, it's not always easy process. And additionally, if the series is convergent, how we can find the sum, like it is convergent to what number? Again, that's even more complicated. We did learn a couple of types of the infinite series, like for instance, geometric or telescoping. And in this situation was quite like we get nice pattern, nice formulas, and in case of convergence, we can find the sum. And this is just because the formula for the partial sums was relatively easy, and then the behavior at infinity, which is limit the infinity, was easy to compute. But it's not always the case. Especially it is not easy, not only computing the limit, to finding the formula for the partial sum. Sometimes we do not have this nice geometric property or the telescoping, and it will be complicated. That's the reason that we need to develop tools, maybe more general tools, but we have to get something to determine convergence or divergence, since it's an important question to be answered. We will develop a couple of tests. Okay? And let's start. Today we will focus on integral test. Also from the sequences, yes, from the first section, we remember another, I hope, another property, another theorem. Then if the series is increasing, sequence. If the sequence is increasing and bounded above, and we remember bounded above, then these conditions guarantee the convergence. It means now when we look at this infinite series with positive terms, we may think about the partial sums as an increasing sequence, because we will be keep adding positive terms. That means we increasing, yes? The terms could be different, yeah? The terms each self, a sub 1 and a sub 2, a sub 3, they might not be increasing, but the partial sums, the addition of the first two terms, the addition of the first three terms, four terms, the partial sum will be bigger and bigger, increasing. And now, if we will manage to prove that is also bounded above, then that the sequence of the partial sums is convergent. And then the series is convergent. Right? I mean, that's what we will use it. And this is just the summary. If we have infinite series with positive terms, we know that it's increasing, the partial sum. The partial sums are increasing. Then, and if we will prove that the partial sum is bounded above, then the series is convergent. If the partial sums is not bounded above, then it's divergent. Okay, I think that's what we will try to use it. And just to be clear, even if the infinites, even if the partial sums are bounded, yeah, that means we can say it's definitely bounded, because when we let's say we will add the first two terms for this alternating series. 1, -1, it's 0. And then when we add 1, 1, and then again subtract 1, that means we oscillating, the partial sums oscillate between 0 and 1. And it is bounded, however, it's not monotonic, it's not increasing. And that's why we will be not able to use it in this scenario. Let's start. What I have. I have just this infinite series. Let's start our investigation looking at the addition of the reciprocals of the squares of the positive integers, 1 over n squared, 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, and so on. Definitely the terms are positive. Great. And now we will, yes, we will try, but we will actually not try, because finding the partial sum, it's not a simple task. But we know we're looking for different tools. What I have a little bit of numerical proof. Let's see the values in the table. N is number of terms. And then on that right-hand side column is the partial sum. When we add 5 terms, yes, 1, 2, 3, 4, 5, S sub 5, it will be 1.46. When we add, for instance, 50 terms, 1.62. When we add 500 terms, partial sums, S sub 500, 1.64. 1.643, 1.6447. It is increasing, but we may notice it's bounded. Yeah, I mean, this is just the numerical. We will do the proper investigation. That's what we can say in general. This series is definitely convergent as n goes to infinity, the partial sums is approaching like 1.64. Even if this is a huge number, even if this, I can say n goes to the infinity, then the partial sum S sub n is approaching 1.64. We will be keep adding, but will never be greater than 1.64. I mean, it will be 1.6, 1.64. Okay, I mean, it's definitely convergent, but let's look at closer. Let's look at some like graphical, because geometric has nothing to do with the geometric series. It is not geometric. We know, we can recognize geometric like arguments, graphical arguments. Okay, so what I will take a corresponding function. The infinite series is the infinite series is 1 over n squared. Okay, but I will look at the function 1 over x squared. Right? That means this is a function. I draw a function just in the first quadrant because n, the domain, is positive, and I create these rectangles. Right? You may notice 1, 2, 3. Each, the base of this rectangle is 1. That means I'm jumping by 1. And then if we will think about the areas of these rectangles, it's base times height. Height is the value of the function, because we can see this is value of the function at 1, value of the function for 2, value of the function for 3, and so on. I mean, 1 base times the value of the function, it's the area. We don't have to multiply by 1, of course, we're not changing anything. And that means these values are the areas. When we add these areas, that's our infinite series. And that's when I have this couple of notes. Okay, and that's we can see when we adding these areas, that's our summation, that's our infinite series. Now what we can do, we may use a little bit of the knowledge from improper integrals. I think that was section 7.7. Improper integrals. Let's take this integral 1 over x squared dx from 1 to infinity. And as we remember, it was convergent to 1. Was convergent to 1. Now, if we think about the integral, integral means function is positive, that's and if the improper integral is convergent, we may think about the areas. That means integral represents the entire area under the curve 1 over x squared. That means represents starting from 1. That's we may exclude at the moment that first value 1. That means everything. Okay? That means now, if I will try to compare the values, the green area is 1, going to the infinity. Not mine, or our infinite series is just these golden boxes, golden rectangles. And the golden rectangles are less than the green area. And that means this is 1 over x squared dx from 1 to infinity. And let's exclude this for a second. We can always add, because we're starting, we know that it's from 1. That means this green area rectangle is It's bounded. It's one. No. It's one. It's convergent. It's convergent. Our golden boxes are less because we can see less. This is greater. This is greater. That's what we're proving. Definitely the partial sums are increasing, but it's also bounded above, because it's never greater than 1. Or if we add this, yeah, I can add, just to be consistent, I can add that one. That means I will be adding 1. That means this is less than 2, thinking about the first value. Yeah? So we can see, we prove through this improper integral that summation is less than 2. It's bounded. It's increased. That means this partial sums is increasing and bounded above. Then we may say the infinite series is convergent. Okay. And we did use the integral. Okay, that's me. Now I can say this partial sum is less than 2. Well, we can see we have to just add this, less than 2. And then I have just, it's definitely increasing, it's bounded above. Then the infinite series is convergent. So we can see when we will keep adding, the sum will be never greater than 2. We actually know from the table above that it's approaching 1.64. Oh yeah, it is less than 2. So we had this numerical proof, and now we have this using the improper integral. We did get some comparison. And that will be the way to use the integral, and we will call integral test. But let's actually look at the other case, and then we will make a summary. Okay, it's me now. Just to, yes, clarify, this infinite summation is less than 1. And it's also interesting. It's also interesting because even we know that this value is approaching 1.64, I mean the entire summation. We also have another interesting number, which was developed by Leonhard Euler, that this summation is approaching that value, pi squared over 6. Okay, amazing. If you will use the calculator to get, it's probably close to this number, even more accurate, because pi, of course, it's, yeah. That means this is the most accurate. Interesting, but we will not investigate why this is, but it's definitely true. Okay, what we did, we know that it's less than 2. And it's big, yeah, it's a big proof. Okay, now let's look at the example number 2. We will take similar, I mean, let's see, 1 over square root of n. Reciprocals of the square root of the positive numbers, 1 over square root of 1, square root of 2, and so on. And now let's think. Definitely each of these terms it's smaller. Partial sums is increasing because terms are positive. But what is happening when we will actually keep adding 2 terms, 3 terms, 4 terms, 50 terms, 100 terms? Is the sum like convergent to a certain finite number, or maybe it's exploding and it's getting bigger and bigger? Okay, that's what I have. I do have a numerical proof, just a little bit, up to 5,000 terms, and we may notice as we increase number of terms, the partial sums, it's getting bigger and bigger. Yeah, we can see 3, 5, 12, 18, 43, 61, 139. So we may guess that if we have more and more terms, this will be not a finite number. So this series is divergent. But let's use our integral approach and prove it. Okay, the same thing. I will take now the function 1 over square root of x. 1 over square. I will build the rectangles a little bit different because you may notice I use the left-hand side. This is just for the purpose of proving, because otherwise we will be not able to prove. But the same thing, the areas are defined as 1 base times height. Height is the value of the function, which is 1 over square root of x, square root of 1, square root of 2, square root of 3. And these golden areas, now we see they are greater than the integral. And let's recall the integral from 1 to infinity, 1 over square root of x dx. I hope we remember. I can maybe rewrite this square root of x as a power of x to the power of 1/2. And that p-value, if it's less than 1, the integral is divergent. Okay, that's what we can say. The green area, divergent means like huge in this case. It's expanding to the infinity. And our rectangles, meaning our infinite summation, infinite series, is even greater than that infinity, if I can say this informally. Then we're proving that this is definitely divergent. Let's see. In this integral from 1 to infinity, 1 over square root of x dx, this integral, improper integral, diverges. We may think like it's infinity. And that left-hand side, the golden areas, the golden rectangles are even greater. That's mean, let's think, let's just use the common sense. Something greater than infinity. Big number, it has to be even greater. This will prove that these partial sums are actually expanding to the infinity. The series diverges. Let's actually see, I have this. The total area is greater than the area under the curve. So we have this. That means this is huge and this is even greater. And we also know from section 7.7 improper integrals that this is, this integral diverges. Because I mean this is the proof, this is the proof that is divergent. Okay. It means the area under the curve is infinite, the sum of the series must be infinite, the series is divergent. Okay, that's what we can do. I was showing you these rectangles, the proof for the case of convergence, divergence. But what we have to take away from this, we have to take a tool. That's one important message. We have to use the tool. The tool will be called integral test, and we do not need to prove it. Okay, we do not need to prove it. What we have to know is this. The integral test. Okay, first of all, if we even allowed to use the integral test, yes, but function must satisfy this condition. Function must be continuous from 1 to infinity, must be positive. We remember the function was always, we draw it above the x-axis, everything gets positive, no continuity, meaning no gaps, no holes, no jumps, no asymptotes, vertical asymptotes, and decreasing. The terms were getting smaller and smaller, the terms of the sequence that we adding them. That means that conditions, if we satisfying, then we can only, if we think the formula is good, we may only integrate. Improper integral. And if the improper integral is convergent, then it will guarantee that the infinite series, the corresponding one, it's convergent too. Otherwise divergent. Okay? That's when you don't have to draw it. The proof will always work if the improper integral, let's say, is divergent, then the corresponding series is also divergent. That's it. And I have a couple of notes. We may use integral test if eventually we're not starting from 1, we're starting from different value. It's fine because we're looking at the behavior at infinity. That we may skip a couple of finite terms at the beginning, from 1 to 4, from 1 to 40, doesn't matter. And actually note 2 also is talking about this because we have to have a decreasing function if the function is ultimately decreasing, meaning that from some point, not from the beginning, not from 1, it's also fine because dropping a couple of finite terms is not affecting infinity. And the most important notes, even if we using this comparison, integral, improper integral convergent, then the infinite series convergence, divergent, divergent, but they are never the same. Yes, we just comparing, and you probably remember from the proof that we just saw it, it was inequality. Like this one was less than 2. That's we comparing to this one, but we know that it's always different. They are not the same. Yeah, please remember that box because it's good true and false question. It's never the same, but comparable. Okay, let's maybe solve 1 or 2 examples and to finalize this integral test. Okay. Test the series for convergence or divergence. Yeah, when we will see this formula, you may think, you may look what test we know. At the moment, we are a little bit limited, but I will look at this one and I will say, okay, test for divergence doesn't work. Because we remember a test for divergence. Do I have, okay, actually I can write this. If we will compute a limit just of this 1 over n squared, limit at infinity, of course, it's 0. If it's 0, we know nothing. We do have a chance for convergence, but we know nothing. That means test for divergence is not applicable. Also, this is not a geometric formula. It's not a geometric because geometric has like an exponential form. That means it's not geometric, okay? The next tool that I have is the integral test. Integral test. Let's try. It means I will look at this, what we can say. Let's say, first of all, this one. Okay, that means now we have to check if a sub n is continuous. That means this is definitely continuous function defined everywhere from 1 to infinity. That means this is continuous. Continuous on the interval from 1 to infinity. Now it's a sub n positive. Yes, it is positive. Because this is always positive for the values from 1 to infinity. And now the third condition, it has to be decreasing. It's a sub n decreasing. We will not, yes, let's actually on, yeah, that means it check, decreasing. It's always a little bit, we have to be careful. But we can see this formula is relatively easy to say when we will create the next term, a sub n plus 1. It means a sub n plus 1. We will increase the denominator. Increasing the denominator, we decreasing the entire term. That means this will be smaller and smaller. That means, yes, this is decreasing. If we we are not sure, we may use the derivative to prove decreasing intervals where the function is decreasing. Okay, that means we satisfying, in this situation, we're satisfying all of the conditions. We may try to apply integral test. Integral test, okay? And probably I will be using IT as a shortcut. What we can do, we may integrate from 1 to infinity 1 over x squared plus 1. It's improper integral, then infinity we will replace with t and we will indicate that t goes to the infinity. Okay, and now we all know what's the integral of 1 over x squared plus 1 is arctangent or inverse tangent, arctangent of x from 1 to t. Now let's evaluate from 1 to t and then evaluate the limit. Arctangent of t minus arctangent of 1. Arctangent at infinity, because t is infinity, is pi over 2. Arctangent at 1, tangent for what angle is 1? Pi over 4. We do have a finite number. Half minus quarter is a quarter, pi over 4, but we don't even need that number. As soon as it's finite, we know that this integral converges. converges. If the improper integral converges, then this infinite series converges. That's what we can say is convergent. And we always have to say what test? By integral test. Everything works. Okay? Convergent by the integral test. And we remember that summation will be not pi over 4. It will be close, will be approach, but who never is identical. So we will never say that this is the summation. No, this was the tool. And we know the rectangles, we definitely prove this is true. Okay, let's maybe do another one. And that's the solution. I type it. Okay, determine whether this series is convergent or divergent. Natural log of n over n. Let's just put maybe 2. Okay, starting from 2 to infinity. Okay, this means this one, again, test for divergence will not work because the limit is 0. It's not a geometric one. The only tool that we have so far, integral test. But let's first of all investigate. Natural log of n over n. A natural log is defined for positive numbers, n is positive. That means this formula, oh, I'm just writing, this formula is definitely positive. Oh, continuous, it's fine. Positive on the interval from 2 to infinity, because I just changed. It's continuous. We do not have any gaps. Continuous. Okay, and now, is this decreasing? This is a little bit extra decreasing. It means since it's not like obvious to determine whether the next term is smaller. Yes, we don't know. It's definitely positive, definitely continuous, but we have to take extra step to prove decreasing. We may rewrite this as a function, natural log of x over x, and basically the question, find the intervals of decrease. We will find the first derivative, critical points, and find the where the derivative is negative. If the derivative is negative, then function is decreasing. Okay, derivative, quotient rule. Derivative of ln of x is 1 over x times x minus natural log of x times 1 over x squared. I mean, derivative is simply 1, because this is 1 over x times x, 1 minus ln of x over x squared. And now, denominator is always positive. That's when it's not affecting the sign of the derivative. Then I will find out, first of all, where the derivative is 0, or the critical numbers, because 0 is not in the domain. Then let's solve this. Let's just solve this. It's 1, then x is e, because natural log of e is 1. Okay, that's, we do have a critical number e. Let's place it on the number line. And when I will test the sign of the derivative, let's say this is the derivative. When I will substitute, for instance, e squared, natural log of e squared is 2. 1 minus 2 is negative. And when I will take square root of e, it will be 1/2, 1 minus 1/2 positive. That means, let's actually see, this is the sign of the derivative. Then function is increasing and then decreasing. Starting from e is decreasing. Okay, and e is 2.71. And we actually operate, when we talk about the infinite series, only with we're looking for the positive integers. And that means if x is e, then the first integer after 2.7 is 3. That means what I will do, I will maybe change everything from 2 to 3. And you may see, I was gonna put 3, but I was waiting for this. You may sometimes see that the formulas that involve natural log of n it will start from 3. Why? Because all of the conditions are satisfied after E, and the first integer after E is 3. That means now we're good. Now this is decreasing because we can see this is the decreasing interval. It means start on the and it's fine. We remember ultimately decreasing. We are not worried, because if I will just check this situation, from 1 or from 2, from 1 to E, from 2 to E, it will be finite number. Yeah, that's definitely convergent. Losing couple of first terms doesn't affect the infinity. We have to check what is going on from 3 to infinity. Okay, that's mean now we actually good to use the integral test, and let's integral test. Okay, let's integrate. Let's say from E, doesn't matter. From E will be maybe easier. From E to infinity, from 3, it's fine. But for the integral, I can use E. I can use 3, I can use 5, 6, the same thing. Natural log of x over x. Natural log of x over x. Okay. What we need the limit, first of all, from E to t goes to the infinity, natural log of x over x. And we know that we can use the u substitution. When I will let u to be ln of x, du is just 1 over x dx. It's sitting and waiting 1 over x dx. That means it's just ln of u du. Let's integrate. Integral of u du, this is u, is just u squared over 2. And let me come back to natural log. Limit as t goes to the infinity, u squared will be natural log of x squared over 2 is times 1/2. Then I can keep my original limits from E to t. And let's see what's happened. It will be 1/2 natural log of t squared minus 1/2 natural log of E squared. And t is infinity. And what we see, natural log at infinity actually goes to the infinity. This is finite number, it's fine. ln of E is 1 actually, 1/2. But this is taking the lead. The improper integral diverges. Okay. Since it diverges, then infinite series also diverges by, my writing, let me write for my students a little bit nicer, diverges by IT, integral test. We always have to state the test, and we have proof, like we proved everything. Okay? And that's how you can keep working. If you will see the formula and you think you might integrate, check all of the conditions, check, positive continuity decreasing, and then integrate. Yeah, we know how to integrate. And if the integral diverges, the infinite series diverges. If it's convergent, converges. But if in case of convergence, the sum doesn't correspond exactly to the sum of the series. Okay, yes, enjoy your integral test. Thank you.